Okay, so we have been talking about the electric field as far as we've done a lab where you mapped some field lines. So now we're going to dive a little bit more into what is the electric field and what do field lines look like. So, an electric field, let's define that word first. The electric field is the force field around an electrically charged object. So, we're going to learn about some of the properties of the electric field. So, we can visualize the electric field. What I mean by that is that if there's an electric field, so if there is an electric field, it will cause alignment. And we can draw the electric field. So, if I have a positive charge, my electric field points away. That's how I would draw my electric field. If I had a negative charge, my electric field points inward. So, what the electric field actually tells us is the force that gets exerted on a positive charge. So, for instance, if I put a positive charge here, it's going to move away. If I put a positive charge here, it's going to move inward. So, we can calculate the electric field. So, if I have a test charge Q and it has a magnitude of some F, a force magnitude of some F at a given location, the electric field at that location, here, let's actually do this first. To calculate the electric field. I have the electric field being equal to the force on a positive charge divided by the amount of charge. So I symbolize this with E equals F over Q. And my units are in newtons per coulomb. which makes sense because I measure a force in newtons and I measure the charge in coulombs. So I can also determine then the force due to an electric field. So to find the force due to an electric field, it would make sense to do F is equal to E times Q. Now these arrows overhead, remember, just mean that is a vector, so it has both a force and direction, and the units are in newtons because it is a force. So let's see here and let's try an example. So, example 1. I have a uniform electric field with a magnitude of 4.6 times 10 to the 4th newtons per coulomb, and it points in the plus x direction. And I want to find the force if I have two parts to this. A, I'm going to have Q being equal to 2.8 microcoulombs. And in B, I'm going to have Q being equal to negative 9.3 microcoulombs. So, I can look then at a drawing that I'm going to create now, where I have some field lines, right? The electric field goes this way, because it points in the plus x direction. This is my electric field. I'm going to have some little charges here. I'm going to have this one being representing part A, and this one down here is going to represent part B. Okay, so A, we know that the electric field lines are going to point in the direction that the force is going to exert on the charge. So my force then is going to be in this direction. I know that. I just don't know what number it's going to be. And down here, remember, negative charge, oh, that's a really curvy arrow. Oops. A negative charge will point in the direction that is opposite the electric field. So, there's its F. Now, calculating these is quite simple. We just use the equation that we had above. So, for part A, the force is going to be equal to the electric field. So 4.6 times 10 to the 4th newtons per coulomb times the charge. So times 2.8 times 10 to the negative 6th coulombs. That is going to give me, sorry, 0.129 newtons. And we know it's going to be in the plus x direction. For B, I just do the same thing. Again, my charge is still, or my force, sorry, my electric field is still 4.6 times 10 to the 4th, and my charge is negative 9.3 times 10 to the negative 6th coulombs. And that's going to give me 0.428 newtons in the minus x direction. And I would know that it's going to be in the minus x because the field is in the plus x, my charge is negative, so it's going to move against it. All right, so next thing we need to talk about is we need to talk about point charges. So we talk about point charges a lot. It's the simplest way to look at this. So the simplest example of an electric field is the field produced by a point charge. So, if I have a positive charge Q at the origin, so if this is my little graph, oops, and I have this little positive charge Q, I'm going to say it's positive, okay? And then I put a test charge, Q0, and let's suppose that Q0 is also positive, and it's some distance r. So this distance doesn't really matter. The force that it experiences obeys Coulomb's law. So the force that Q0 experiences because of Q is given by Coulomb's law. So that means the force is K Q Q0 over R squared. Same thing if I replace this Q with a negative charge. So I can find the magnitude of the electric field produced by a point charge. So to find the electric field produced by a point charge, well, let's look how I would get this equation. Okay, I know that E is already equal to F over Q naught. But I just said that F is equal to this thing. So I can go K Q Q naught over R squared over Q naught. What that does is it gets rid of my Q naughts. So it's K times Q over R squared. Now remember, Q is the charge and R is the distance squared. So here's a quick example to show this. So if I have a 1 microcoulomb charge and I want to find the field at a distance at 0.75 meters. All I have to do, remember, is plug it into this equation up here. So E is equal to K. which is still 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. The charge is 1 times 10 to the negative 6 coulombs. And the distance is 0.75 meters, and I need to square that. So this meters squared goes away. This coulomb squared, the squared goes away, and I just have coulombs left. When I calculate that out, I get 1.6 times 10 to the 4th newtons per coulomb. So, the distance, or the field, this is important, the field due to a point charge rapidly decreases as the distance increases. It will never approach 0, but it will get extremely close. All right. Now, this is a really long section. Sorry, guys. I don't know, though, how much I had to do with that. Okay. So, electric fields can add together, and they add together by superposition. So, when a system contains several charges, the total electric field is found by superposition. And what I mean by that is superposition is just the vector sum. And we've done a lot of that. So if I have this system. Okay, here's my XY coordinate plane. Always useful to work with when I'm talking about vectors. And I have Q1 up here. And it's going to have a charge of plus Q. And I have Q2 down here. And it also has a charge of plus Q. I want to find the charge, the total field at point P. Okay, so I'm trying to find the total field at point P. Now, I know that this is some R, and that that's going to produce some electric field because of charge 2. And I also know that this is some R, and it's going to produce some electric field because of charge 1. But I need to find my total field. So I need to find E total. Okay? Again, I've got some thetas in here. Here's theta. And because they're the same distance away, these two angles should both be the same. Okay, so I've just sketched the drawing. This is because of symmetry that I can say that the two angles are the same. So, since the two charges have the same magnitude and distance from P, E1 is equal to E2. So, because R1 is equal to R2, E1 is equal to E2. And because Q1 is equal to Q2. So I can find the E's, right? I can say that E1 is equal to E2 is just KQ over R squared. So I can find X and Y components now. This is something that I'm pretty good at doing, or have done before at least. So my electric field total in the Y direction is going to be equal to, oops, not sum, E1 in the Y direction plus E2 in the Y direction. Now, the difference is one is below and one is above. So, I have negative E sine theta plus E sine theta. Because they're equal in magnitude, just opposite in direction. So this is just going to be equal to 0. So I have no electric field in the Y direction in this case. I can do the same thing with the X direction. So E total in the X direction is E1 in the X direction plus E2 in the X direction. Now this case, they're both the same. So E cosine theta plus E cosine theta. So it's just 2E cosine theta. So the total electric field, because I have 0 here, now if I was to find E total, I would have to do the square root of E total Y squared plus E total X squared, which in this case I would still just get 2E cosine theta. Alright, now this one is going to be a little bit different. We're going to do an actual example with numbers this time. And the positionings are also different. So, here we go. Here's my example. Now, we're going to say that in this case, Q is 5 microcoulombs, and R is 0.75 meters. Here's my drawing again. Okay, I have an X and a Y plane. Okay. I'm wanting to find the magnitude at the origin. This is my point P this time. Okay. So, I have two charges. I have a charge up here, which is going to be negative Q. And I have a charge over here, which is also going to be negative Q. I know that I'm going to have some EX and some EY here. So I know that E total is going to go off in some direction, right? So, this is going to be R, and this is going to be R. So, I know that because Q1 is equal to Q2 and R1 is equal equal to R2, that E1 is equal to E2. Just makes things a little bit easier when I can say that. So let's go ahead and find our E in the X direction. EX is KQ over R squared. So 8.99 times 10 to the 9th times 5 times 10 to the negative 6 over 0.75 squared is going to give me 8 times 10 to the 4th newtons per coulomb. Now remember, this one is only going to produce in this direction. This is going to be EY, which is going to be the same as E1. And this one is going to be EX, which is the same as E2. Because this can only exert in one direction, and this can as well. But I also know that EY then is the same as EX because I just said this. So I have 8 times 10 to the 4th newtons per coulomb as well here. Now, to find the totals, remember, I do the square root of EX squared plus EY squared. And I would find that I have 1.1 times 10 to the 5th newtons per coulomb. Alright, so we have some rules for drawing field lines that we're going to talk about real quick, and then we will be wrapping up this section. So, drawing field lines is another important part of this section. So, rules for electric field lines. We saw earlier that they start at a positive charge or infinity, and that they end at a negative charge or infinity. We saw that up here. Okay, over here, they're starting at a positive, ending at infinity, starting at infinity, ending at a negative. Okay, so, oops. The third rule is that they point in the direction of the field vector E. They point in direction of field vector E. Okay, they are closer together where E is a bigger number. So where it has a greater magnitude. And the number of field lines is proportional to the charge magnitude. And we'll see what I mean by that in just a minute here. So, if I want to draw, I'm going to make my positives and negatives different colors because I think it makes it a little easier. So if I have a charge that is plus 2q and another charge that is simply minus q, this one should have twice as much, the plus 2q should have twice as many lines coming out of it as the negative q. So, this is going to wrap around, You might get one over here. But remember, they go into the negative charge.